the first of today's worksheets. So this is 8.1 lecture worksheets. In looking at the chemistry of water, we have to start by understanding why water is a polar molecule. So water, we understand the shape already, is a V shape, but the second half of why water is setting up how life exists on planet Earth is that water is a V shape, but also the second half is that water is a polar molecule. And it is a polar molecule because it has polar bonds. And so this starts off by looking at what's called bond polarity. So bond polarity, you will see, is the name polarity is very similar to the next worksheet we're going to talk about, which is molecule polarity. Now, don't get confused though, they are very different concepts. So bond polarity has to do with the distribution of electrons in one bond. So there's two electrons in one bond, and that's it. We're just talking about where those two electrons are. Do they spend more time on one atom versus the other atom in the bond? That just is that bond. Now, when we go on to molecule polarity, this has to do with the electrons in the entire molecule. Okay, so this molecule polarity, which we will get to, we're not going to start with though, it starts off with understanding the bond polarity. Even though the word polarity is in both, the way bond polarity is determined is very different from the way molecule polarity is determined. And that's because bond polarity is only the electrons in one bond. So that's two electrons in the one bond, compared to the molecule polarity, which is the electrons in the entire molecule. Okay, so polarity basically is used in both because it describes where the electrons are. Are they on poles or are they even? So that is the definition here in bold, is if you have electrons, those two electrons in the bond equally shared is called a non-polar bond. And so if you've ever shared something with someone, let's say you share a kitchen with someone. So two people share a kitchen. Is it equally shared where you're in there 50-50, or unequally shared where someone's in the kitchen more than the other? Okay. Or if we're actually talking about something that's shared like an object, well, does that object, is it 50-50 shared between the two people, or does it spend more time with one person than the other? So if you have an unequal sharing, this is called a polar bond. And when that object is with the one person more than the other, there's in the bond equivalent, the electrons are what are shared, and they spend more time on the more electronegative atom. And so this is the bond polarity is determined by a very simple calculation. It's called the electronegativity difference. So electronegativity, or EN, is what I used for short. And electronegativity is basically the attraction an atom has for electrons in bonds. And so each atom has its own ability to attract electrons, and that's why each atom's electronegativity values are not the same. So hydrogen's 2.1, lithium's 1.0, beryllium's 1.5. There's general trends of these electronegativity values. You can see like lithium 1.0, and then beryllium 1.5, boron 2.0. This electronegativity increases going across, or electronegativity also increases going down a column. And there's general trends because electronegativity is related to the atom's sizes. And so that you don't really have to know, just know that each atom has its own individual electronegativity, and you use these electronegativity values for reference. So you don't need to memorize these, but you do need to know where to find them so you can use them to calculate what's called the electronegativity difference. Okay, and so the electronegativity difference is subtracting the electronegativity value of one atom compared to another atom in the bond. So you can only have two atoms in a bond. A molecule might have 5 or 10 or 30 atoms, but an individual bond only has 2 atoms. Okay, so if you have a molecule with 5 or 10 or 30 atoms, what you have is each bond has a calculation for the electronegativity difference. You can only do the calculation for 2 atoms. Okay, so the 2 atoms in the bond. So that's number 1. Number 2 is these upright brackets. This is called the absolute value. And I mentioned in the video, the upright brackets means absolute value, which means whatever the number is, the subtraction, make it a positive number. It's never going to be a negative number value. Okay, so that's all you need to know. You need to know where to find those electronegativity values. You're only going to have 2, subtract them, make the number positive. Then you have the number will either be in a range of 0 to 0.4, and that's going to be a non-polar bond. Okay, so that's what that says, less than or equal to 0.4. But you're never going to have a negative number. So that means the range is 0 to 0.4. Okay, or the range is 0.5 in between 0.5 and 1.9. That's a polar bond. And the polar bond is the bond that is unequally shared. And so a polar bond from the video, you can draw dipole arrows. You can draw a dipole arrow, and that dipole arrow points to the more electronegative atom. And so what do I mean by the more electronegative atom? Well, the 2 atoms have electronegativity values. And if the value falls in the polar bond range, that's 0.5 to 1.9, that means the one atom will have a higher value for electronegativity. And so the arrow will point to that higher value electronegativity. So instead of being a line, you would draw it as an arrow. Okay, so I'll show you this for these examples. So first you want to determine the bond polarity, which is for the HF bond, the electronegativity difference is going to be equal to the absolute value of hydrogen is 2.1 and minus the fluorine 4.0. And then the upright absolute brackets is that 2.1 minus 4.0, if you put in your calculator, ends up being negative 1.9. Okay, because you take the absolute value, it's 1.9. Now, what do you do with that number? You figure out where it falls. It's either in this range. Let me highlight this in green. It's either in this range or this range. Okay, and so 1.9 is in the range of a polar bond. It's 0.5 to 1.9. So the polar bond needs to point to the more electronegative atom, adding a dipole arrow. And so this hydrogen fluorine, the fluorine is the higher value. So this is 4.0 compared to 2.1. So notice that the arrow point is towards the fluorine, which means the electrons spend more time on the fluorine. And that is also this, you can draw as a partial negative on the fluorine because the electrons spend more time. So this means partial negative, that kind of cursive D, that's a Greek lowercase d delta. And this is partial negative compared to the hydrogen, which has the electrons less of the time, and that's a partial positive. So let's take a look at the nitrogen hydrogen. Okay, so the nitrogen hydrogen, the electronegativity difference is nitrogen, the value for nitrogen is 3.0, and the value for hydrogen is 2.1. So the absolute value is going to be 0.9. And so that is already a positive number, so just 0.9. That also falls in the range of a polar bond. So that polar bond, you can draw instead of the line as a bond and H, you want to redraw that as an arrow. And so where's the arrow going to point to? The more electronegative atom. And so you go back and look at those values. This one was the nitrogen, which is 3.0. So that one gets the arrow point because 3.0 compared to 2.1. So nitrogen's the more electronegative atom. It would be the partial negative compared to the hydrogen would be the partial positive. These arrows will become important in the next step, understanding the molecule polarity. Okay. For now, though, we'll just add those arrows. So for the oxygen-hydrogen bond, the electronegativity difference is the value for oxygen 3.5 minus the value for hydrogen 2.1, and that is 1.4. Okay. And so the reason, remember, for the bracket, the absolute value, is you'll always end up with a positive number, no matter which calculation, if it's 3.5 minus 2.1, or if it's 2.1 minus 3.5. No matter the order of the subtraction, you'll always end up with the same number value, but the absolute value makes it a positive number value. So 1.4 is in the range of this polar bond range. So a polar bond means that the electrons are not equally shared. So this electrons in this bond will spend more time on the more electronegative atom, and the higher value is that 3.5. This is the oxygen value. So this you can draw as an arrow pointing towards the oxygen, which means oxygen has the partial negative and hydrogen has the partial positive. Okay, let's take a look at nitrogen and oxygen. The electronegativity difference is the nitrogen value is 3.0 and the oxygen value is 3.5. So 3.0 minus 3.5 will give you negative 0.5, which will be just 0.5 as the absolute value. And so that again is in the polar bond range. Many of these fall in the polar bond range because it's a wide range, 0.5 to 1.9, compared to the much smaller 0 to 0.4. So that's a polar bond, which means you could draw this as nitrogen and oxygen, but turn that bond into an arrow pointing to the more electronegative atom. Which atom has the higher value this time? The 3.5. So that was the oxygen. So the arrow points to the oxygen, which means the oxygen is partial negative and the nitrogen is partial positive. Okay, and then let's take a look at the hydrogen and hydrogen. So when you have the electronegativity difference and the atom is exactly the same, you're just having the same number, 2.1 minus 2.1, which will give you the absolute value of 0, which is just 0. Okay, and so what's 0 fall into? 0 falls into this range, 0 to 0.4, and that is the nonpolar bond. So for the nonpolar bond, this is the hydrogen bonded to the other hydrogen. This one, you have no dipole arrow. Okay, so if it's polar, yes, you add the dipole arrow pointing to the more electronegative atom. But for a nonpolar bond, you have no dipole arrow. You leave it as just the bond, just the line. Okay. Now, how do you handle this molecule? So here's a molecule CCl2F2. You might remember this as the chlorofluorocarbon that is, we learned about this in impacting the ozone layer. So this is the chlorofluorocarbon structure. So there are 5 atoms in this. Do we subtract fluorine from chlorine from carbon? No, you can only do the electronegativity difference for one bond at a time. Okay, so there's 4 bonds in here. So this is the carbon chlorine bond. And we can do the electronegativity difference of that. And it's the same as this other carbon chlorine bond. Okay, so that is going to be different from the other type of bond, which is a carbon and fluorine bond. So the carbon and fluorine bond, highlighting this in green, is a different bond. So this is a CF bond. Okay, so you don't calculate, you can never, or in this electronegativity difference, you should never be subtracting more than 2. So not 5, not 3, just the 2 atoms in the bond. So identify the bonds that need calculating, and then you can continue on if you have more atoms in your molecule. So first, the carbon chlorine bond. So the carbon chlorine bond, moving this up so I can look up what carbon and chlorine are. Carbon is 2.5 and chlorine is 3.0. Okay, so carbon is 2.5. And this is the electronegativity difference here of carbon and chlorine is 2.5 and 3.0. So this is going to work out 0.5. that is a polar bond. Okay, so I'm actually going to add the dipole arrows directly on this molecule. So which is the more electronegative? The 3.0 is the higher value, which is the chlorine. So that means the arrow points towards the chlorine. So turning that bond into an arrow. Okay, so that means there's partial negative on each of those chlorines. Now the carbon fluorine bond. So we need the electronegativity difference. And so we need those values for carbon and fluorine. So let's roll this up and look up carbon, which is 2.5, and fluorine is 3.0. So this is 2.5, sorry, not 3.0. I think fluorine was 4.0. So 2.5 minus 4.0, and this will end up being 1.5, which is also a polar bond. Okay, so if it's a polar bond, you can turn the bond into a dipole arrow, pointing to the more electronegative atom. The higher value is 4.0, and that would be the fluorine. Okay, so the fluorine. Let's do this on the molecule. So this points to the fluorine for both of those bonds. And so that means fluorines are the partial negative. And the carbon in every one of those cases is the partial positive. So all those electrons spend more time on those outer atoms compared to the center atom, because the outer atoms are the more electronegative. And so that'll factor into the molecule polarity, which we'll get to. But first, you got to understand bond polarity is just a simple calculation between the two atoms in a bond by looking up their electronegativity difference, and then these ranges, the nonpolar bond range or the polar bond range. Okay, got that? We're going to move on from bond polarity, as promised, into molecule polarity. So you're down with bond polarity. That's the electronegativity calculation. Well, molecule polarity is different. So the starting point is looking at the bonds that are polar and adding dipole arrows. Okay, but the dipole arrows are added to the shape of a molecule. And so those are going back to those Vesper shapes. So though we are in the second half, and I said, you're going to need to remember a few things from the first half, this is one of those things, and that's Vesper shape. Those are molecule shapes. We will definitely be looking at molecules, continuing to look at molecules. Those are those molecular views, because that's what we have in nature, is these molecule shapes that determine so many things like nutrition and why one COVID molecule or one COVID vaccine works and the other doesn't. It has all to do with molecule shapes. So we were going to start with the molecule shapes and include the bonds, specifically the polar bonds. Polar bonds with the three-dimensional Vesper shape. Let me stick the word Vesper in there. So that's the Vesper shape. That's the three-dimensional molecule shape called the Vesper shape. That is what you look at to determine what's called the molecule polarity. And the molecule polarity is the overall distribution of electrons. And so the overall distribution of electrons is different from just the electrons in one bond, okay? So there is going to be all the bonds, there's also going to be lone pairs, and we have to look at all of it on the entire shape. So the first thing you do in figuring out the molecule polarity is start with the bond polarities. So start by calculating the bond for every individual bond. So you can only do 2 atoms at a time, and this is basically a short version of what we just did in the first worksheet. You have electronegativity values, you look up those values, you calculate the electronegativity of the atoms in the bond, and then you figure out what range does it fall into, nonpolar or polar, okay? And then when you turn those polar bonds into dipole arrows, that becomes arrows on a shape. And so you will have arrows pointing to the more electronegative atom. If you have double bonds or triple bonds, those lines, every line becomes an arrow. And remember that you have no dipole arrows if it's a nonpolar bond, just like that example we looked at that was nonpolar. There was no dipole arrow with those 2 hydrogens. So you don't always add dipole arrows. You only add the dipole arrows if you have a polar bond, and a polar bond is in this range, 0.5 to 1.9. Okay. And so when you have the arrows on the shape, then you look at all of those arrows in total and you think about it being like a tug of war. Like, okay, this arrow is going this way, this arrow is going that way. If they're going in exact opposite directions, that's called a pull, an overall pull. And the pull will either be overall towards one direction or another direction, because you can add up the directions of the arrows, or those arrows pulls will cancel out. And you saw those examples in the video. And so when there is no overall pull, because the pulls cancel out, that will lead to what's called a non-polar molecule. So this is if those pulls or the arrows cancel out. And the polar molecule is when you do have an overall pull. So when the arrows don't cancel out. Okay, and so it is important to note that the molecule polarity is not at all the same as the bond polarity. You are looking at arrows on the shape. So it's not the same, even though it has the same word polarity in it. So when you are looking at when you have some lone pairs on the central atom, this is step 5. This is always going to be a polar molecule. This is those lone pairs on the central atom are 2 shapes, the bent shape and the trigonal pyramid. So bent is 2 bonds and 1 or 2 lone pairs. Trigonal pyramid is 3 bonds and 1 lone pair. Those always have a lone pair on the central atom. And when there's lone pairs on the central atom, the molecule is always going to be polar. And that's regardless of whatever happens with the arrows, because lone pairs indicate an uneven distribution of electrons. There are electrons in one part of the molecule, but not another part when you have lone pairs on the central atom. Okay, so there's this is number 1 is first you're going to be looking at the arrows, but there's also a default. If there's these particular shapes, they're always going to be polar no matter what, if there are arrows or no arrows. Okay, so let's take a look. You're given the shapes of these molecules and you have to just add the arrows, right? So step 1 is determining the bond polarities. So when you have the nitrogen and oxygen bond, you want to calculate that electronegativity difference. So you need the numbers for nitrogen and for oxygen. I'm just going to put the absolute value brackets and then scroll up to look and see that nitrogen is 3.0 and oxygen is 3.5. So this is 3.0 minus 3.5. And so this is 0.5, and 0.5 falls in this range of the polar bond. So 0.5 is a polar bond, which means point a dipole arrow towards the more electronegative atom. So which is the more electronegative is the higher value, the 3.5, which is the oxygen. So this would be an arrow pointing towards the oxygen. So turning these bonds into arrows. So this is an arrow pointing towards the oxygen. That double bond gets 2 arrows. This single bond also gets just the 1 arrow. Okay. And so you have arrows that are pointing left and right, but more importantly, all 3 of these arrows are pointing down. So there is an overall downward. If you add all of them up, there's an overall downward pull. It's left and right, but there's this downward component that you can add up. So because there's an overall downward, or you can also think there's no canceling out, there's no upward canceling any of these out. There's an overall pull. And when there is an overall pull, this is a polar molecule. Okay, so let's take a look at the next one over, which is OF2. So you have the OF bond. Oops. So this is the oxygen fluorine bond. The electronegativity calculation is going to be the number values for oxygen and fluorine, which are oxygen is 3.5 and fluorine is 4.0. So this is the absolute value of 3.5 minus 4.0, which is 0.5. And 0.5 falls in that polar bond range. So this is a polar bond. which means that you could turn this bond, this line, into an arrow pointing to the more electronegative atom. So 4.0 is the greater value. So this means the arrow points towards that fluorine. So that means turn these bonds on this shape into arrows. Okay, so both of those. So notice this is the bent shape that you were given. This was also the bent shape. So all I did was point those arrows because the fluorine is the higher value, and you still have an overall downward pull. So both of these are downward. There's no upward to cancel out. So when there is an overall pull or push downwards, this is going to be a polar molecule. Okay, and also remember that anytime you have a bent shape, the molecule will always be polar because of the lone pairs on the central atom, whether they're drawn there or not. Okay, so this is the H2O molecule. So this is the hydrogen-oxygen bond that you need the bond polarity calculation. So you need the number values for hydrogen and oxygen. Hydrogen is 2.1 and oxygen is 3.5. So this is the absolute value of 2.1 minus 3.5, which will give you 1.4. So this is a polar bond range. It is between 0.5 and 1.9. And so that means you can turn those bonds into dipole arrows. So pointing to the more electronegative atom is the pointing towards the oxygen because it was 3.5. So it would be this, hydrogen pointing to oxygen. So turn those bonds on the shape, which is also a bent shape, into arrows. And this time you have both of those arrows are pointing in. They're left and right would cancel out, except for there's an upward component. So there's an overall upward. Okay, so overall upward pull. And when there is an overall pull, this makes this a polar molecule. Okay. So let's take a look at the next example, which is CO2. So this is the carbon dioxide molecule. And you can see that given that shape, it's the linear shape. Okay, you have a central atom with bonds on both sides. This is a double bond on this side, double bond on that side, but central atom with two bonds is linear. So first, let's add the bond polarity for the carbon-oxygen bond is going to be the calculation of carbon and oxygen. So go back up and look for the electronegativity values of carbon and oxygen. Carbon is 2.5 and oxygen is 3.5. So you have the electronegativity difference, 2.5 minus 3.5. So that works out to be 1.0, and that 1.0 falls in the range of a polar bond. Okay, so when you have a polar bond, turn it into a dipole arrow pointing to the more electronegative atom. So 3.5 is the higher value. So this would be the oxygen gets the arrow point. So turn those bonds on the shape into arrows. So this is an arrow to the oxygen twice because it's a double bond, and same thing on the other side of the carbon, arrow to the oxygen twice. And what happens with all those arrows? So these arrows are going left and right, and they're going left and right with no up or down. So these arrows cancel out. So these arrows will cancel out. And because they cancel out, that makes this a non-polar molecule. Okay, so now here's an interesting comparison. You can have a polar bond, and polar bonds can give you a polar molecule. In all these examples above, polar bonds gave you a polar molecule. But here, this is a polar bond that gave us a non-polar molecule. Okay, so those polar bonds don't always yield a polar molecule. Because the shape is linear, those polar bonds canceled out and gave a non-polar molecule. All right, let's look at the next examples. These are both tetrahedral shapes. So this is the tetrahedral shape. That is the tall pyramid Vesper shape. It is the central atom with 4 bonds. And this is a base of 3 with a tall top. Now, one thing to remember about the tetrahedral is that you have this coming out front and this going out back. And so it is not a shape with three. It is really in 3 dimensions. The way to draw this is that they're all equally 4 different directions in 3-dimensional space. So that's why you have to add this to remember that it's not just 3 on the bottom. It's 3 going in 3 equally spaced apart directions. Okay, so remembering that about the shape, now let's add the bond polarity. So this is the CBr bond, the carbon and bromine bond. We need the numbers for carbon and bromine. So going back up, the electronegativity values, carbon is 2.5 and bromine is 2.8. So this is 2.5 minus 2.8, which is 0.3. 0.3 falls in the range of the nonpolar bond. So what do you do if you have a nonpolar bond? You have no dipole arrows. Remember that example from before? A polar bond is when the electrons are unevenly shared. They spend more time on the more electronegative atom. Well, nonpolar bond is when the electrons are evenly shared. They spend time evenly, 50-50. So there is no arrow. Okay. And so that means keep those bonds, don't add any arrows. And so now what do you do? Because remember, the step is you have to look at an overall pull of those dipoles. Well, what do you do if you have no arrows? Well, that means you have no pull. And so when you have no pulling, no arrows, that leads to automatically a nonpolar molecule, as long as you don't have the shape that has lone pairs on the central atom. Okay. So remember this number 5, if there are lone pairs on the central atom, those are the shapes that are bent and trigonal pyramid. It's always going to be a polar molecule, no matter what's going on with the bonds. Well, as long as you don't have the bent or trigonal pyramid, this is a tetrahedral shape. That means this can be a nonpolar molecule. So in this example, you had a nonpolar bond leading to a nonpolar molecule. Okay, so the bonds are not always going to be the same as the molecule. And let's take a look at this next example of CCl4. We have the same tetrahedral shape, but this time the bonds are carbon and chlorine. So the carbon and chlorine bond, we need to calculate the electronegativity difference. So looking for carbon, which is 2.5, and chlorine is 3.0. You have the absolute value of 2.5 minus 3.0, which is 0.5. So 0.5 falls in the range of the polar bond. And the polar bond means that you do add dipole arrows, and the dipole arrow points to the more electronegative, the higher value, which is 3.0. 3.0 is the chlorine, so the arrow needs to point to the chlorine. So this time on this tetrahedral shape, I'm going to take those bonds and turn them into arrows, and they are pointing towards the chlorine because that's the more electronegative atom. That's the higher value. Okay. And so this is arrows pointing in all 4 different directions in 3-dimensional space. What happens to those arrows? So that's what's important to remember about the tetrahedral shape, is that this arrow is going out front. This other arrow, one arrow is going out back. One's up and one's off to the side. Well, those are going in equally 4 directions. And so what this means is that these arrows will cancel out. Even though it looks like, wait, you've got 3 going down at the bottom, but remember, this is not all just 3. It's one going out front and the other going out back. They will actually cancel out on this tetrahedral shape, which means when the arrows cancel out, when the poles will cancel out, that is going to be a nonpolar molecule. And so in this example, you had a polar bond that results in a nonpolar molecule. And so you can see here that the bond polarity, even though it's polar, will give you a nonpolar molecule because of the shape. Okay, and so that's why these are different concepts. The bond polarity is different from the molecule polarity. Okay, any questions? Representation. This is the water molecule that has the Lewis structure. We talked about the Lewis structure. This is the two-dimensional shape that has the central atom with 2 bonds and 2 lone pairs. But because there are 2 bonds and 2 lone pairs, so 2 bonds and 2 lone pairs, it's not a linear shape in 3 dimensions. When we move into the 3-dimensional Vesper shape, it's this bent or V shape. Okay, and so that's super important, because if water were a linear shape with those 2 polar bonds, so those are polar bonds, and that's the dipole arrows. If water were a linear shape, those 2 polar bonds would cancel out. So see how those 2 polar bonds, those dipole arrows pointing towards the oxygen, because oxygen is more electronegative, those bonds would cancel out on the linear shape. But because it's a bent shape, those bonds do not cancel out. And so this results in a polar molecule. Okay, and that's why if water were linear, those bonds would cancel out and would be a nonpolar molecule. Well, that would be a problem. If water were nonpolar, we would not have all of the properties that we know about water, which start with the hydrogen bonding. But we have a polar molecule because of the bent shape. And this bent shape, here's the space filling, or this is called the molecular view. Okay, you'll see all of that. We have water being a polar molecule. And with the molecule polarity, water can dissolve other polar molecules. So those are polar compounds, and water can dissolve most ionic compounds. And this is because water forms hydrogen bonds. So what exactly is a hydrogen bond? It is when the partial negative part of water, so that partial negative is the oxygen, will be attracted to the partial positive on a different molecule. So actually, I'm going to erase that, is that you have the hydrogen is the partial positive. It is attracted to the partial negative on a different molecule. So it can never be within one molecule. So even though you have partial positive and partial negative on one molecule, the partial positive and partial negative for hydrogen bonding has to be between other molecules. So when water forms a hydrogen bond, it is going to be to a different water molecule or a different polar molecule or a different ionic compound. Okay, and so adding the partial positive, so partial positive, remember, is that delta plus sign, and the partial negative, remember, is the delta negative. Let's add those dipoles on these 2 water molecules. So you have to have separate molecules, and that's the attraction of the partial positive to the partial negative. Okay, so for the water molecule, let's add that. So remember the water molecule, this is the oxygen. I'm going to actually add this as the color red. Oxygen is the central atom for both of these. These are both water molecules, and those are red. That didn't turn out on the black and white. Okay, and then these are the hydrogens. Okay, so this will to orient you and remind you that the hydrogens are the partial positive dipole, and the partial positive is going to be attracted to the oxygen that is the partial negative dipole. And so remember, that's here. Oxygen is the partial negative, hydrogen is the partial positive, hydrogen is the white, that's this guy, oxygen is the red, that's that guy, but it has to be on 2 separate molecules, 2 different or separate molecules. Okay, so the attraction of the partial positive is attracted to a partial negative on a different molecule, and it's shown with a dashed line. Okay, so a dashed bond or dashed line. Instead of a bond that would be just a line, the dashes mean that it is an attraction, not a bond. Okay, so it is an attraction, not a bond. So dashed line instead of the word bond. And so that's this dashed line that I'm highlighting in blue there. And that is the attraction of one water molecule to another water molecule. And that specifically is the hydrogen bond. So this is the hydrogen bond. And in the video, I'm going to put bond in quotes because it's not actually a bond. It is not a line. It is a dashed line because it's an attraction. So it's an attraction. It shouldn't be called a bond, but it is. And it's called hydrogen, not because it's two hydrogens that are bonded together, but it is a hydrogen on one molecule that is partial positive and it is attracted to a partial negative on a different molecule. Okay, so that's the definition of a hydrogen bond, is the hydrogen is attracted to an oxygen, nitrogen, or fluorine on another molecule. And so water can form these hydrogen bonds to polar molecules that have the partial negative can be an oxygen, nitrogen, or fluorine. And so here's a molecule that is not water. This is ammonia. This is NH3. So this is NH3, and it is a trigonal pyramid shape. Remember that shape, which is a low pyramid. It's the base of 3. So one hydrogen's in the plane. One hydrogen is out front. That's what that thicker line means. And then one hydrogen is going out back. That's what that dashed line means. Well, this is the trigonal pyramid shape, and the nitrogen hydrogen bond there's 3 in this molecule, 3 nitrogen hydrogen bonds. The nitrogen hydrogen bond is polar. And so we could draw this as dipole arrows. And so the dipole arrows here are going to be for the nitrogen hydrogen bond, pointing to the nitrogen. The nitrogen is the more electronegative atom. Okay, and so this would be these dipole arrows pointing to the nitrogen. And that means that the nitrogen is the partial negative atom in the bond. So this is the partial negative, is because the nitrogen has the electrons more of the time, because nitrogen is the more electronegative atom. And so that means also that the partial positives are the other end of the arrow, the hydrogens. Okay, so if hydrogen is the partial positive, that partial positive hydrogen is attracted to a partial negative. And where can that partial negative come from? Well, if we want to draw the water molecule being the partial negative attracted to the ammonia molecule, where is the partial negative on the water molecule? Well, remember, water has the partial negative is the oxygen, and this is oxygen that is a hydrogen bonded to 2 hydrogens. This is the partial negative oxygen. And those hydrogens, oops, sorry, didn't mean to do that. Keep that red. And those are hydrogens that are also bonded to the oxygen. So the partial positive here on this ammonia molecule is attracted to the partial negative on a different molecule. This is the water molecule. So you got the partial negative on the water, which is the oxygen, the red, and this is attracted to the partial positive. So this is the hydrogen bond right there. The hydrogen bond, you want to remember, is not a bond. It is the dashed line. Okay, so that's that dashed line, not a full line, but a dashed line. And it is between the partial positive, let me circle that in green, to the partial negative of a different molecule. Okay, and so when you have water is attracted to other polar molecules, it is the partial positive of water to the partial negative. And this is going to add also, let me add here, the partial negative of this molecule. That's the ammonia molecule, can also be attracted to the partial positive of water. So the partial positive of water is the hydrogen. So that's the hydrogen, and that's a different water molecule than this water molecule. This is the partial positive hydrogen that is attracted to the partial negative of the ammonia. That's on the nitrogen. Okay, so you can have a hydrogen bonding of different, the water molecules. You have to use different water molecules when you're attracting the partial positive or partial negatives within that one ammonia molecule. Got that? Okay, so let's take a look at this water. Water molecules can also be attracted to ionic compounds, and this is an example of sodium chloride. So over here, you've got the sodium ions and the chlorine ions. This is sodium is a full positive, and chlorine is a full negative. And so how this works for the water molecules. So adding in water molecules, adding in the attractive forces, is a negative is going to be attracted to the dashed line to a partial positive. So what is the partial positive when you're talking about the water molecule? Well, the partial positive is the hydrogen atom of the water molecule. And so that would be that H2O water molecule, okay? So when you have the sodium that is a positive ion, what would a positive ion be attracted to? A positive ion is going to be attracted to a partial negative, and that, when you're talking about water, is the oxygen part. So the oxygen is the partial negative of this water molecule. That's that bent shape. And that's that partial negative is the dashed line to that positive. Okay. And so what that means is when you have a whole bunch of positives and negatives in this NaCl, sodium chloride, that's the greens and the whites, how are we going to align all of those water molecules? So the water molecule overall is going to be that V shape. So that V shape, just as a V, just drawing it as a V without the atoms in there. Remember that in that V shape, you have the partial negative is the pointed end, and the partial positives are the open end. Okay. And so if we're going to add the water molecules on all of this, the way this is going to look is you have the partial negatives are the pointed end. So the pointed ends are going to be attracted to the positive sodiums. But the open end, the partial positives, these guys are the open end of the water molecule, that V shape. So the negative chlorines will attract the water molecules this way as the open end. So see how that's very purposeful. You have the open end versus the pointed end. Well, what happens is that water will dissolve this ionic compound by surrounding. So all these are water molecules that surround. They come in and they surround the sodium and the chlorine, those positive and negative ions. And so these are all water molecules that come in here. And every single V I'm drawing is a water molecule that is aligning with those ions based on the positives and negatives, aligned to the attractions to the partial negatives and partial positives. And so the surrounding of those ions happens and literally pulls these ions off one at a time. Okay. And so eventually you would have a sodium ion. This is a positive sodium that is surrounded by individual water molecules. I'll draw those in red that are, oops, no, this is the alignment is going to be with the pointed end of the water molecule. That's the negative end. And then a chlorine will be surrounded by, so chlorine ion will also be surrounded by water molecules, but the alignment of those water molecules around the chlorine is different. It's the open end. And so why is it the open end? Because the open end is the partial positive end of the water molecule. Okay, so remember that. This is the water molecule. You have oxygen and hydrogen. The hydrogen is the partial positives and the oxygen is the partial negative. And so that's why this is the open end. Those are the positives that are around this negative. And this is the pointed end. Those are the negative end around that positive. Okay, so do you guys follow all that?